connection and then apply a very thin bead of solder to secure the wire forever in position. Remove the enamel coating from the second wire and solder it to the other connection, like before. Be very careful not to drip the solder down onto the enamel wires below. This could cause an electrical short. When you're done, it should look something like this, and then we're going to take a piece of electrical tape and isolate at least one of these wires so that there's no way these two wires can touch during vibration. We're going to go over this with some shrink wrap shortly, but we want to make sure that we don't have a short, so we isolate this from themselves. It should look like this, and we are going to finish this off with some shrink wrap in just a moment. Now we're going to test the electrical connections to make sure that our coil is going to use the right amount of electricity and make sure that we don't have any kind of electrical short circuit. Trim the main wires back, and we're going to get a multimeter, and we're going to check and see how many ohms of resistance are in our coil. If you don't own a multimeter, that's okay. It is alright to skip this step. We're just showing you exactly what's going on. It has a reading of 26.6 ohms. Now what this number allows us to do is calculate the exact amperage that we'll be pulling. Current is equal to voltage divided by the resistance, which we know is 26.6 ohms. We know that we're running 14 volts. We do the math, and it comes out to about 0.526 amps, or half an amp. That's how much power we're going to use. Power is often expressed in watts. So what we do to calculate the watts is multiply our half amp times the 14 volts, and it comes out to about 8 watts of electrical energy that our coil will be using. Now this thing operates in a vacuum state. It does very little at atmospheric pressure, but once the air has been sucked out of that tube, it acts much like a radio tube. We're able to apply a magnetic effect to the oxygen and the hydrogen inside this tube, and the stronger the vacuum, the more the effect will be. This tube will get hot with use around 130 degrees Fahrenheit. So even if you don't have a meter, you can hook this up, and after several minutes you should be able to feel a warmth moving through the coil. Now we're going to apply a safety coating over the electrical tape and the wires that we've already covered with something called heat shrink tubing. You can find this at a hardware store or an electrical supply place. When you heat this tube, it will actually shrink. It's really difficult to find a large diameter piece of this stuff, so I'll show you how to stretch it out and make the most of it. Don't try to heat this and stretch it out, because that is going to defeat the purpose. It would only get smaller on you. Stretch it out with a pair of needle nose like this, and you should be able to pull it far enough up on the line to cover everything securely. It may take several stretches to get it just right. Push the shrink wrap tubing up over the electrical tape all the way up to where the wire clamp is holding the wire. Then you're going to want to take a cigarette lighter and heat this. Careful not to get it too hot in any one spot. Just spread the heat around and you'll see it shrink into position very quickly when you apply heat. Our finished connection will look like this, and we'll have plenty of area to stick this into our vacuum system. The other end of our coil is also going to need a small piece of heat shrink tubing. We cut us a piece off, and we do the same thing to this end of the magnetic coil. Be careful not to overheat this tube. Also stay away from the enamel coating on the red wires. When you've finally completed your flux magnetic heating tube, it's going to look just like this. The total cost on this thing is only about $7.50 to $8, depending on where you live. Now these wires that we use to connect will eventually degrade, as well as these alligator clamps. Now we get a lot of life out of the wires, but this alligator clamp, especially the positive terminal, is just not going to live that long. We found it's just easier to solder this on and off and replace it periodically. You can get quite a few of these very reasonably priced, and it seems to just be a replaceable component. You just twist it off, put a new one on, and you're good to go. Always replace the positive. It's just a good idea. It will degrade much faster than the negative. The negative hardly degrades at all, but it will too also need replacing periodically when needed. This is truly the meat and potatoes of the fuel cell: the magnetic flux vacuum tube line, the circuit breaker, the wires, and the fuel cell stack cups. You don't want to run your fuel cell above 150 degrees if you can help it. Now, the size of your jar is very important, and you have to work on your fuel cell because of the anodes. Now, the anodes are the cups that are on the outside, the positives. They're going to degrade, so you're going to be in this. Now, what makes these things degrade? And what chemical is in this water? What turns this water brown like this? Why does it taste so good? Well, actually, it doesn't. Don't do this. But we're going to find out. I'm going to a laboratory. We're going to see. And we've driven our water-burning truck to a laboratory to get this water analyzed directly from our fuel cell.
Kind of warm.
Yeah, I just got through.
That'll affect the slope on the pH.
We drove it straight in the parking lot right to this laboratory to get a true reading on the pH level of our fuel
37
cell
degrees
water.
Celsius. Actually, it's quite basic.
Really?
pH is over 10.
Is that, well, that would be
Well,
on the,
it's the opposite of what I thought it would be. I thought it would be an acidic, looks like a lot of, well, there's a lot of suspended solids floating around in it, so that means that can happen when the pH is above 8.2. Iron comes out of, dissolved iron comes out of solution at pH 8.2 and forms an insoluble particle that might explain the color and the high solids content that you can see. When it stops flashing, it shows the actual pH.
so that's the opposite of what you thought it'd be.
Yeah, I thought it'd be an acidic solution.
But it's actually an anti-acidic solution.
Oh yeah, it's the opposite. Each
So it'd be alkaline then.
yeah, very alkaline. The pH scale 7 is neutral, and each increment is exponential. It's a multiple of 10. So at a pH of 7, going up to pH 8 is 10 times as basic as 7. 9 is 100 times more basic than 7.
All right.
And 10 is, what is it, 1,000. Yeah, it's 10, hundreds. Each time it's exponentially greater. So this is,
So you're actually stirring that with a little magnet thing.
yeah, it's a magnetic stir.
Wow.
That just keeps a flow going over the surface of the glass.
Yeah, I see some of those
product.
solids in there. Wonder what those solids are.
We'll do an iron test to see if it's iron. Of course, I was wrong before. That's why I assumed it was pulling iron out of the
Right.
electrode that you had.
Interesting.
With a sacrificial anode, I guess is what it is.
It's getting even more alkaline, looks like.
Well, it's just trying to stabilize. The more particles you have and
Right.
going across the top, it can kind of make it unstable a little bit. The temperature is kind of leveling off at 37.3 degrees Celsius. But it's very basic. pH is approximately 11. Trying to second guess it is pretty tough. That's why you got to do the test.
Right.
Undoubtedly, his test is more complicated than mine. However, we both came to the same conclusion. This is a non-acid substance. Now we're going to find out just what those solids are. Those solids that appear in your fuel cell have actually been the source of a lot of controversy. In a vacuum state, a lot of particles appear and disappear in the quantum vacuum. So some of those materials may get trapped in our universe in that vacuum state, in which case they would definitely appear in the fuel cell eventually sooner or later. Now we can't test for every chemical, we just don't have the time, but we can definitely test for several of these chemicals to find out just what this stuff is.
Fine.
Right.
I don't know what the range on this test is. See, this only goes to 3 milligrams per liter. I bet this will go off scale, over range.
We'll see. Surprised you before.
Well, yeah, it might not be any. Read. Over range.
So we can
So
definitely say that
it's over 3 milligrams per liter. So, which I could kind of tell by the color.
Right.
But the only thing you can do it now is cut it. So what it is now, cut 10 to 1.
See, I only
here we go.
used just little pieces.
So move the decimal point over. That's showing a little bit under 7 milligrams per liter iron.
Okay.
That is an extremely high iron content.
Really?
It's actually cutting it this with the math. It would be somewhere around 6.8 milligrams per liter iron, or 6.8 parts per million iron. So because we cut it 10 to 1, so you multiply it times 10, just move decimal place point over, milligram per liter
Right.
iron.
So
this is
very irony.
ferrous iron with deionized water with 0 iron. And this is the raw sample, which went off scale uncut. We had to cut it 10 to 1 to get it where the spectrophotometer could shoot a beam of light through it and give us an accurate sample. The photometer machine only goes to 3 milligrams per liter, which said this was almost 7.
Right.
6.8 milligrams per liter. So we had to cut it 10 to 1 and do the multiplication. So you lose a little bit of accuracy there, but I mean,
Right.
it just tells you it's like
Ballpark.
6 or 7 milligrams per liter iron. I mean, that's what it is.
So pretty much what we're doing is we're using water that is 22 times more irony than river water. It didn't start that way. It started out as normal tap water. Now, physicists like to tell me I'm actually using more power than I'm creating. I can prove this is wrong with a power inverter, and I'm going to shut the hydrogen off to it. Watch what happens to my power inverter. Suddenly, I no longer have enough energy from my motor at idle to run my power inverter. This thing has to have a certain amount of power, and I've turned on all my equipment in my truck, including my air conditioner, fan, blower, headlights, to put this load on the engine. Now I'm going to open the hydrogen back up to the engine, and there you go. Now, it's not the vacuum leak that caused this increase in RPM. We've tested this over and over. This is proof that we actually get more power out of the hydrogen than we're putting into it. We're only putting 200 watts of electrical energy into this water to make this hydrogen, yet we're able to pull out more than 1 horsepower of electrical energy in response. Now that just blows scientists away, and it's the source of a lot of controversy, but you can prove it for yourself once you've built and installed this hydrogen-oxygen fuel cell on your very own vehicle. This entire installation can cost less than $100, including all the wiring. The fuel cell itself can actually cost you less than $20, depending on where you get your parts and how good you are at finding a bargain. Now, we've increased the size of this jar to 1 gallon. We do this because in the summertime, if you hit 160-degree water temperature, you're in danger of flash boiling. We don't need that vaporous steam boiling. That's really good for cleaning the engine, but it's not that great for mileage. We're trying to get higher mileage. Now, I'm inserting our magnetic flux line heating coil into the vacuum system, which is tied directly into the brake. That's right, we're using the vacuum line that goes to the master cylinder. It won't affect our stopping. We plug this into our fuel cell jar, and we're going to hook the power leads directly to the fuel cell contacts. This is an easy way to do this. You can do this much better later and find a much better place to put this coil wire. I highly recommend a switch for this coil because even though it only uses 8 watts of electrical energy, it does a tremendous job at exciting the hydrogen and oxygen fuel. And on this truck, which has no knock sensor, it tends to cause it to burn so lean that in the city, I just can't use it without getting motor knocking. So I turn this coil off until I hit the open road where I can lean back my engine and save that fuel. It is true, a car's computer will affect your performance, and if you make too much hydrogen-oxygen gas, your performance can degrade instead of increase. This is because of the O2 sensor on the car. But this magnetic flux heating coil line that we've just created will help to neutralize that effect. Most of this problem occurs on deceleration. We have the most intense vacuum. During this intense vacuum, our coil works much better because of the vacuum charge on the 3/8 plastic line. That magnetic field will charge that hydrogen and oxygen gas where it will burn better with our hydrocarbon fuel. We won't have as much leftover oxygen, which usually causes the O2 sensor problem. Your computer results may vary with your car, but generally speaking, your car will perform much better running hydrogen-oxygen gas. Just please try not to run this over 160 degrees Fahrenheit. I'm going to hook my magnetic coil right here on my fuel cell power connections. It's already fused, and it's very convenient because it's located right here. You just have to make sure that you maintain a good connection on these at all times, and it can be a little bit tricky when you're hooking these up to jumper cables, but this is a great way to test it. Now, a lot of superheated energy is going to be going through this coil, and it will get very hot, but it should not melt this line. If you see any tube melting, or if you're pulling more than a half amp, you definitely have problems. Now, when you first start your gas, it should be very lean, just like you see right here, because the pH level, as we know, will increase from the destructing anode over time. We're going to be running it through this coil, putting 8 watts of electrical energy into this hydrogen-oxygen gas in the vacuum state as it travels into our combustion engine. We have the vacuum pressure, which will increase the efficiency of the hydrogen-oxygen production, and as it goes and gets warmer, we will have more and more gas. As the vacuum increases, we will have more magnetic effect from this line counteracting bad oxygen and creating, hopefully, para-hydrogen, which is just an amplified form of hydrogen. This truck has been burning hydrogen-oxygen fuel for over 2 years and gets 24 miles per gallon on the highway and has as much power and performance as it did the day it was made. Oil changes have to be made less frequently, although you do have to maintain your fuel cell, and it is a lot of work and it's not for everybody, but the performance is there. This is not an illusion. Now, I'll tell you, you just don't want to run this thing in the city unless you're moving. Shut it off because you don't want to hit 160 degrees. Smaller fuel cells that have less water will actually hit the 160 degree threshold sooner. So a cell like this is great for winter weather, but could be a problem in summer when under the hood the temperatures can get very hot and this heat could transfer to this water and you lose your efficiency. This design should perform very well in very cold climates. If you get into warmer weather, you just increase the size of the jar and decrease the amount of baking soda you use. In a 60-ounce jar like this, you'll use less than 1 gram of baking soda. That's about 2 aspirin-sized pieces of baking soda in this amount of water. And this is the amount of bubbles you want to see. Don't get carried away, because once you start the engine and the vacuum condition takes place, this will multiply. Also, we're at room temperature right now with this water. The pH level is about 8 or 8.2. It's going to increase as the anodes destruct very microscopically over time, and by the time we burn this water, our pH level will be around 11. We'll be carrying a lot more current than we started with, so you start this thing out really lean when you're using regular water. Now you see the 1 gallon jar. This jar is tremendously more efficient at staying cool. The vacuum pressure from the engine will actually cause this jar to lose temperature. That is to say, if it was 140 and I started the engine and took off, it would actually fall to around 132 degrees Fahrenheit. As long as I kept moving, the temperature would not rise. The larger jars offer a lot of benefits over the small ones in warmer weather. Now this orange that you see is proof that our pH is now over 8.2. You can add a temperature probe to this so that you know what's going on. Just put the probe on top and add 20 degrees to whatever the reading is. That'll give you a good approximation to the actual water temperature, and you won't have to have a probe inside. Just add 20 degrees and you'll have a very good approximate temperature of what's going on. Now, we've installed cameras under our hood, and we've tested this fuel cell going down the highway, because frankly, bench tests are absolutely worthless. When you're sitting there looking at your fuel cell, you just don't have the inertia, the airspeed, and the amount of power that you have when you're going down the highway. So fuel cells just cannot be tested on the bench. If you're really hardcore into fuel cells, you can actually install a baby monitor to visually watch your fuel cell as you're going down the highway. It's how we learned all the things that we've learned about our fuel cell. Watching, driving, and measuring performance levels and measuring miles per gallon. We hope this information is helpful, because understanding what's going on can help you use a fuel cell effectively to get the performance that you need. If you've got a vacuum leak, you've got a problem. So vacuum is important. You can see the vacuum as I'm going down the highway. I'm traveling at 50 miles per hour. Now when I push on the gas pedal, the balloon will actually get smaller. And when I let off of the gas pedal, the balloon gets larger. Now this is contrary to what you might think. In other words, we have less vacuum whenever we are taking off or accelerating. And that means that we have less hydrogen-oxygen gas. Now, some people have installed dual lines, one to the carburetor with a check valve. However, I've found that there's just not enough vacuum from my carburetor to accommodate this line, and it's absolutely worthless on this engine. I still find all the results I need by simply tapping into the vacuum line on the master cylinder of my vacuum system, which travels directly to my combustion engine, and I see these performance and increases. Now, when you let off of that gas, the water can boil, but only if it hits 160 degrees Fahrenheit. Inside the fuel cell, the pressure reaches a point to where the water is actually able to boil at 160 degrees Fahrenheit because of the vacuum. This is not good, so we just try to use larger jars and less soda. By using less soda, we have less electrical conductivity. About 12 amps is all you really need from a fuel cell when it's running and you're traveling down the freeway. If you have access to high-grade stainless steel, you can have plates made and you can put together these cells. Again, we use positive plates on the outside, negative and neutral plates on the inside. These are the most efficient way that we've found to actually produce this gas. These nuts and bolts are high-grade stainless steel. They're very expensive, and this kind of cell will set you back quite a few dollars. These plates, you can actually reverse the polarity and they will self-clean. These plates are really thick, very heavy, and they will last a long time. You can put a lot of energy through these cells. They will get hot if you do so, but they will make a tremendous amount of gas in the process. So reversing polarity is a very good idea on this kind of cell, often to clean them. If your fuel cell is very tall, then more than likely the water will eventually not be reaching all of the plates, so the amperage will change. So keeping your fuel cell completely submerged is a very good idea. You can see the tremendous amount of production that we get off of these flat plates. This is much higher grade stainless. It's going to last a much longer time. There will be cleaning necessary, but it's really not that difficult to do. And we do save a tremendous amount of fuel when we use these cells correctly. Now, this water is actually very cool. So, as we run the cell, the temperatures will increase. We do not want the temperature of this cell to get any hotter than 150 degrees. So we run it with vacuum. If we find ourselves stopped at a stoplight for a long time, we're probably going to want to shut the cell off because our motor will tend to run too rich under those conditions. We just don't need this much HHO gas all the time. At least not with a computer controlling our combustion. You see the water coming out of the tailpipe. Every successful installation I've ever seen, there was always vapor present coming from the tailpipes. The amount of water vapor that you see from your pipes is going to vary with the pipe length, the temperature, and a lot of other factors. But basically, when you start your engine, you run it on HHO for about 5 minutes or so, you should see some water vapor coming from your tailpipe. And when we increase the RPM, and increase the suction pressure, we see a white fogging of the fuel cell itself. This is a brand new cell. It's clean, and it's not going to look this way very long. We're going to show you this cell when it reaches full temperature. When the cell reaches its full temperature, which is about 150 degrees, the HHO bubbles in this state of vacuum are very large. The production is very high, and the boiling effect that you see, which is not steam but HHO, is very intense. This intense boiling requires a dryer on the front end of this as a gravity stop for the water to prevent it from going into our vacuum line. We don't need to ingest water into our vacuum system. The water that you see coming from the tailpipe is a product of burning HHO. The hydrogen and oxygen molecules recombine in the state of combustion, and they will form water. This is distilled water. Do not attempt what you're about to see. I wanted to show you what hydrogen-oxygen gas looks like. And the only way to really see this hydrogen-oxygen gas is under circuit breaker, under safe conditions at atmospheric pressure. I'm catching some of this in some detergent so that I can ignite this and show you some of the explosive power of just a few bubbles of this hot hydrogen-oxygen gas. It's very white, very interesting looking gas. No steam involved. Hydrogen fuel cells work excellent on 4x4s, giving you 5, 6, 7, 8 miles per gallon, or even more depending on how you drive. So we're going to show you a professional installation right here. The electrical is hooked to the battery like this, and there is a 25 amp inline fuse slightly below the battery. Didn't show up there. And we have got this one wired with some stranded wire to a relay, which is going to control this, so we'll eliminate the need to turn it off and on if we so desire to wire it that way. So we can flip a switch, a relay will turn it on. If we turn off our car, it will turn off the fuel cell, so we don't run our battery down, because it will pull some amperage. The amount of amperage will vary with the amount of baking soda you add to your cells. Now here we've used a plate system, a much more advanced hydrogen fuel cell. And these 7-plate systems, we have 2 here, and a dryer in front, right there. That is the dryer. There's no fuel cell there. Hooks right into our master cylinder vacuum line, which hits right into our carburetor on this particular 4x4. So, hydrogen fuel cells, this end.
So those 2 are the fuel cells. That's your dryer. You got yourself a
Relay.
Where'd you power your relay from?
Under the dashboard, you can locate a switch. Make sure you use a very heavy-duty 30, 40, 50 amp switch, whatever you can find. Just make it at least above 25. Alright, now we see where he's actually wired into the power, sending power to his fuel cell terminal block.
That right there is the power for my little relay. It just runs to the switch right here.
This is also an excellent place to install another fuse for safety. 25 amps, if that's what you're going to run it at.
Yeah, that's really wicked.
That's for when I go off-road.
A brass shutoff valve for off-roading.
Yeah, this is a 4x4.
Yeah, got to go off-road.
Because when you go jumping across ditches, you're going to need to protect yourself against the water, which could slosh up into the fuel. So, this is a professional installation. Electrical bus bars for these fuel cells to wire into. We have grommets on our connections. And we have stainless steel clamps which hold the mason jar securely in an acrylic mounting bracket. Very excellent job here. A fuel cell like this should run you about $300 installed. And let me say, most of that is installation, but the wiring can be tricky. If you're not qualified to do the wiring, and if you're confused about the wiring to relay, you really shouldn't attempt this yourself. Find a friend or a mechanic who'll wire it up for you.
Okay, now I notice you're using some what appears to be stranded wire in your fuel cell.
Solid.
Is it?
Yep.
Solid copper wire, very
That
important.
must be number 12 then.
Yes, it is. It's.
Okay.
I can get some number 10, but this seems to carry the current just
I
fine.
highly recommend number 10 wire.
Get some, I'm going to go down to Keithley Patterson and just get about 40 feet red, 40 feet of black.
These fuel cells are catching on. You can find them in many, many cars all over the state already. We start the truck, and instantly the relay closes, and we have hydrogen-oxygen gas entering our engine. Now this is a very high production cell, and the hotter it gets, the more production we'll get. Right now the water is extremely cold and the cell is extremely clean. There is some iron in this water, and it will increase the amount of electrical current over a period of time. In other words, this cell will have to be cleaned, or it will exceed the amperage and blow the fuse. At the tailpipe, now this hydrogen-oxygen gas is cleaning this engine, removing carbon, and may I say, I've never seen any vapor come out of these tailpipes until today, folks. So it's just a matter of time till this engine is steam cleaned and runs like brand new. Everyone who owns a V8 truck needs to know about HHO, hydrogen oxygen gas. We're not talking about water injection here, folks. We're talking about hydrogen oxygen injection. These vacuum fuel cells make a lot of gas. Be careful. Thanks for watching.
Yeah.
Explosion is very unlikely inside this fuel cell because of the vacuum. However, if you were to leave the fuel cell on with the ignition off and it was completely full of hydrogen gas and you started your vehicle and your vehicle backfired, and let's just say that all these things did happen someday, should there be much cause for alarm? Do you think the glass would explode in shrapnel? Well, I found a friend who was willing to light my fuel cell, and we're going to find out just what's going to happen. Now, before we go out with a bang, let me just say thanks to everyone who's worked on the fuel cell for the past 2 years, and thanks to CerseiPress.com and MetalPress.tv. It's been an incredible 2 years of experimenting with vacuum pressure fuel cells, and we think they work just great. Visit the website and join the forums.
You can do it, just spark it, and it's done.
Let's see that again in slower motion. That's an incredible amount of force. Several horsepower was certainly released. The jar did not break. The lid actually stretched these wires out to their fullest extent. The velocity of that lid was several thousand feet per second. The fuel cell stayed in the jar. It actually came loose from the breaker. I cannot stress to you how important it is to keep your head away from the top of the lid. Thanks for watching.
You can do it, just spark it, and it's done.